Okay, so welcome to this next video in which we are discussing the antithrombotic drugs. Okay, right. So we're in the process of looking at the mechanism of the anticoagulant warfarin. Okay, so we've discussed that to produce certain of the coagulation factors, you need to be able to produce this gamma-carboxyglutamic acid, or rather, you need to be able to turn glutamic acid residues within a protein into these gamma-carboxyglutamic acid molecules. Okay, and I might as well just give you the coagulation factors that this is going to be necessary for. So this is necessary for the synthesis of the coagulation factors 2, okay, so prothrombin. It's also necessary for 7, which remember is the starting coagulation factor in the extrinsic coagulation pathway, then 9, which remember is important in the intrinsic pathway, and finally 10, which is important in both. So it's 2 and 10 are the most important there, but 7 and 9 are also very important in the extrinsic and the intrinsic coagulation cascade, respectively. So the way I remember this is that it's similar to the list of cranial nerves which carry parasympathetic fibers. So 3, 7, 9 and 10 are the cranial nerves which carry parasympathetic fibers. Okay, now this is 2, 7, 9 and 10, so it's close. Okay, so it's kind of similar to that. Okay, so if you give warfarin, you can no longer modify these glutamic acid molecules to gamma-carboxyglutamic acid, okay? And it's going to stop the synthesis of these coagulation factors 2, 7, 9 and 10. And remember, 2 is prothrombin, so that's a biggie basically in coagulation. And if you stop the synthesis of those, so their levels are just going to drop off in the blood, so you're not going to be able to undergo coagulation basically. You're not going to be able to turn fibrinogen into fibrin, so you're not going to be able to form thrombi, certainly, because in order to hold the thrombus together, you need the fibrin meshwork to hold the platelets together. If you don't have that, then you've just got to do with platelets, and it doesn't hold together, and certainly isn't capable of occluding blood vessels. But in addition, obviously, this means that you're not going to be able to form hemostatic plugs properly, because your hemostatic plugs that you form won't have any fibrin meshwork and therefore won't be very strong. So my grandmother is actually on warfarin, and if she cuts herself, she just bleeds and bleeds and bleeds. Her blood just does not form a hemostatic plug basically. Hemostasis fails. Okay, so it's a dangerous drug to be on, basically. Okay, right, but it's a very powerful antithrombotic. Okay, and she's on it because she's got a prosthetic heart valve, which is prothrombotic, so it has a tendency to have thrombi form on it. So to prevent that, she takes warfarin every day through oral administration to prevent her liver from being able to synthesize coagulation factor 2, 7, 9 and 10, and therefore prevent coagulation. Okay, so let's discuss the mechanism of action of warfarin then. Okay, right, so to understand how this enzyme, gamma-glutamyl carboxylase, okay, how this works, we need to discuss the structure of vitamin K, because vitamin K is tied up in this completely. Okay, so let's start off by discussing the structure of vitamin K. Okay, so the structure of vitamin K is that you have these 2 aromatic rings. So you have a benzene ring here, and I'm drawing skeletal structures, by the way, so everything I do here will be skeletal structures, so we won't show carbon atoms, and we won't show hydrogens off carbon atoms. So here is our benzene ring with alternating double and single bonds. So it's a 6-membered ring where each of these corners is implicitly a carbon atom, and you will notice that each carbon only has 3 bonds, so that means that there's a missing bond, so that is implicitly to a hydrogen atom, so we don't have to show that. Okay, right, so then what you have is another 6-membered ring attached here, and this is what's known as a 1,4-benzoquinone ring. Okay, so you have 2 carbonyl groups off this ring, one here and one here. So let me just discuss the structure of the 1,4-benzoquinone group over here. So you have a 6-membered carbon ring, you have 2 double bonds here and here, and then you have carbonyl groups coming off both these tip carbons up here. So this is the structure of, and I should have put 1,4-benzoquinone. Okay. So in vitamin K you have this 1,4-benzoquinone group within the structure of vitamin K. Okay. Then off this structure here you have a methyl group, and because we're drawing a skeletal structure, all we do is show a single line, and there's implicitly a carbon at the end of here, and because we haven't shown any other bonds coming off this carbon, the other 3 bonds are implicitly hydrogens coming off there. Okay, and then it has a long tail, so let's draw the tail of vitamin K. So you have 1 methylene group, and then you have a double bond between this carbon and this carbon here. You then have a methyl group coming off down there, and then you have, the tail continues, you have 3 methylene groups in between, and then this carbon will also have a methyl group coming off it here. Okay, and then the pattern continues, so you'll have another 3 methylene groups here. Okay, then another methyl group coming off, another 3 methylene groups, then another methyl group coming off, and then it will end with another methyl group there. So that's the structure of the tail of vitamin K. So this now is the whole of vitamin K. Okay, and you can get this from curly kale and things like that. It's in vegetables. Okay, right. So why is vitamin K so essential for the action of this gamma-glutamyl carboxylase, which is going to add this additional carboxylic acid group onto glutamic acid? Well, basically, it's not vitamin K itself which is essential for that function. Instead, it's something known as vitamin K hydroquinone. So let me show you the structure of vitamin K hydroquinone. Okay, so vitamin K hydroquinone is going to undergo a reaction that is coupled to the addition of that gamma carboxyl group onto glutamic acid. Okay, so the structure mainly remains the same. So here is our benzene ring here. Okay, like so. But what we're going to do is we're going to cleave this bond here and this bond here. So we're going to cleave the the second of the 2 bonds in that double bond there, in both of these carbonyl groups. So one of the 2 bonds that is in that double bond is going to break. And if you imagine, each of these bonds, each of these 2 bonds that we've broken, each of them will have 2 electrons in, one from the oxygen and one from this carbon. Okay, so imagine returning the electron from the oxygen to the oxygen and the electron from the carbon to the carbon. Okay, and do the same here. So this carbon has a free electron, this oxygen has a free electron. Then what you do is break this double bond here. You don't break both bonds, you break the second of the 2 bonds. And again, imagine returning one of the electrons to this carbon and one of the electrons to this carbon. So this, and this all have free electrons. So what's going to happen is this carbon here is going to form another bond with this carbon here. So this carbon is going to use its free electron and put it into a bond, and this carbon is going to use its free electron and put it into a bond, and that will turn this into a double bond here. The same is going to happen between this carbon and this carbon here. So this carbon will provide its free electron and this carbon will provide its free electron and create a double bond there. Then what you're going to do is bring in 2 hydrogen atoms. So 2 protons and 2 electrons are going to come in, and that means 2 hydrogen atoms overall, and you're going to bind these hydrogen atoms to the free electrons of both of these oxygens. So 1 hydrogen will bind to this oxygen, 1 hydrogen will bind to this oxygen. Now that's not a molecular mechanism by which this happens. It's just me helping you keep track of where everything's going and why this reaction makes sense. Okay, so what we now have is we still have this 6-membered ring, but it's no longer a 1,4-benzoquinone. Instead, it's got double bonds here and here, and it's now got 2 alcohol groups at these 2 ends now. Okay, then it's still got the methyl group off here, and then it's still got the tail of vitamin K here. So there's the double bond, here is the methyl group, and then we've got these 3 methylene groups leading on to a methyl group, another 3 methylene groups leading on to a methyl group, another 3 methylene groups leading on to a methyl group, and then that's the end. So there's the final methyl group. Okay, so this is vitamin K hydroquinone that we've now got here. Now, basically, what is going to happen then is if we bring back up our reaction of, in fact, I might redraw this out. I'm going to have to redraw this out so that it's all on the same page. So let me just, in fact, I'll put the R groups. So rather than draw the full amino acid structure here, I'm just going to draw the R groups of the glutamic acid and the gamma carboxyglutamic acid. So I'm going to draw these bits, basically, cut off. Okay, because nothing about the core amino acid structure is changing anyway. And then it will fit nicely in snugly here. Right, so here is the R group of glutamic acid. Okay, so 2 methylene groups and 1 carboxylic acid group on the end, and then it is going to go to this gamma carboxyglutamic acid, which will have an additional carboxylic acid group of this gamma carbon, which is here. Okay, so we're putting another carboxylic acid group here. Okay, right, and then we're putting 2 hydrogens off here, and a hydrogen here. Right, okay, so the enzyme which is catalyzing this, remember, is what's known as gamma glutamyl carboxylase. Gamma glutamyl carboxylase. Right, so it's going to basically couple this reaction of turning glutamic acid into gamma carboxyglutamic acid to a reaction involving vitamin K hydroquinone. Okay, so basically what's going to happen is vitamin K hydroquinone is going to be turned into what's known as vitamin K epoxide. Okay, so vitamin K epoxide. And now let me discuss the structure of vitamin K epoxide with you. Okay, so firstly what's going to happen is that we're going to reform these double bonds between the 2 oxygens. The double bond between the oxygen and the carbon. So what we're going to do is we're going to take away from the vitamin K hydroquinone those 2 hydrogen atoms that we've just given them. So we're going to break the bonds between the oxygens and the hydrogens. So you are going to get off, basically, at the moment, 2 protons and 2 electrons, or just 2 hydrogen atoms, basically. And now both of these oxygens are going to have unpaired electrons because they had paired this electron with the electron of the hydrogen atom that they were bound to. But now that hydrogen atom's gone, so they've got unpaired electrons. So what they are going to do is they're going to cleave these 2 bonds that we've formed here again, okay? So that this carbon and this carbon will both have 3 electrons again, and they can use those 3 electrons to bind with the 3 electrons of the oxygens. So you'll get the double bonds forming again. So let me show this. Okay, so here is the benzene ring. Again, and this hasn't changed at all. Good, this is visible. And then we've got this 6-membered ring here. Okay, and we've now got these carbonyl groups here. Okay, and that's how we've given up these 2 hydrogen atoms again. Right, now you might think, well, surely we're just going to go back to vitamin K. We're just going to reform that double bond here, and everything will be fine, because this carbon's still got a free electron, and this carbon's still got a free electron. But we're going to do rather more than that. Okay, so now I need to discuss this reaction somewhat more. So basically, in order to do this reaction, what you're going to do is you're going to bring in carbon dioxide, okay? So carbon dioxide is going to come in. So where should I put this molecule? So I'll put it here. But what you have to remember is that even though I'm drawing these two separately, they are all part of the same thing, basically. So this is on the same side as the vitamin K hydroquinone. So is the carbon dioxide, and we're going to make this vitamin K epoxide, which I haven't drawn yet, the gamma carboxyglutamic acid, and we're also going to make water. You're also going to take in oxygen. So let me now talk you through everything that's going to happen. So here is the structure of carbon dioxide. Here is the structure of oxygen. Okay, what you are going to do is you're going to take the carbon dioxide, and this again isn't a molecular mechanism, it's not an attempt to be a molecular mechanism, it's just to keep track of everything. By no means is this the molecular mechanism. Okay, so you're going to break one of those bonds between the oxygen and the carbon, okay? And that second of the double bond, that second bond of the double bond, will have an electron from the oxygen and an electron from the carbon. So one electron is going to go back to the carbon and one to the oxygen. Okay, so then this carbon will have a free electron and the oxygen will also have a free electron. What you're then going to do is bind that free electron of this carbon to this carbon here. So you're also going to break this bond between the carbon and the hydrogen. Okay, now this has two electrons in it again, so imagine taking one of the electrons to the hydrogen and one back to the carbon. And again, I want to stress that this is not the actual electron movements, basically. This is just how I keep track of the electron movements and make sense of this reaction. I do not know the actual molecular mechanism by which this happens. Okay, so you imagine taking one electron back to the hydrogen and one electron back to the carbon. Okay, then what you're going to do is use that free electron on this carbon to bind with the free electron on this carbon, and then you'll add on this group basically. But the oxygen also has a free electron, and you're going to bind that free electron with this hydrogen, and then what you'll end up with is this group here. So you've broken this bond here, you've broken this bond here, you're going to bind this carbon to this carbon just like so. You'll have the double bond from the oxygen up here, you'll have the single bond to this oxygen here, and then you're going to stick the lone electron that this one has got with the lone electron that this hydrogen has got, and then you've got this carboxylic acid group. Now, that is not the way this actually occurs. That is a good way of keeping track of what's happening, but you could say, well, that should surely occur without anything to do with the vitamin K hydroquinone being converted to vitamin K epoxide, and I would say you're correct. So that is not the way that this actually happens, but that's a good way of keeping track of how this reaction makes sense. Okay, so we're also bringing an oxygen in here. Okay, so what's going to happen is you're going to break both of the bonds between those two oxygens, and again, this isn't the molecular mechanism. I don't know if I can stress that enough. This is just me keeping track of it and making sense of this reaction. Okay, and then basically what you've got is two oxygen atoms. What you will then do is bind one of these oxygen atoms to these two hydrogen atoms to create water. Okay, so here's water, and then this other oxygen atom will bind that to these two carbons. So these two carbons have got free electrons, so we're going to make one form a bond with an oxygen and the other form a bond with the oxygen as well. And then you've still got your methyl group, and then you've still got your tail of the vitamin K here. Okay, like so. So then we've got these free methylene groups, the methyl group, the free methylene groups, the methyl group, the free methylene groups, the methyl group, and then the final methyl group off up there. So that is vitamin K epoxide there. So I hope you at least understand how this reaction makes sense. So if I now summarize it, so in fact I should write a big equation for this. So let's go on to the other side. So you start off with vitamin K hydroquinone. Okay. You also start off with your normal glutamic acid. So this is vitamin K hydroquinone. You also start off with glutamic acid. okay, a normal glutamic acid, and then you also have oxygen and carbon dioxide. Okay, now what happens is that you convert this to vitamin K epoxide, along with gamma carboxyglutamic acid. So you have done what you set out to do. You have added that carboxylic acid group onto the glutamic acid molecule. So gamma carboxyglutamic acid. Okay, and then you've also created water in the process. Okay, and that is the reaction overall that this enzyme, gamma glutamyl carboxylase, is going to do. Gamma glutamyl carboxylase. Okay, right. So you can see now that in order to add this carboxyl group onto the glutamic acid, you need vitamin K hydroquinone to be turned into vitamin K epoxide. You cannot convert glutamic acid to gamma carboxyglutamic acid without doing this full conversion of all of these things into all of these things, basically. And I hope that what this has done is it's not an attempt to be a molecular mechanism, but it's wrong if it's as far as molecular mechanisms are concerned, but it's just to help you keep track of why everything makes sense, basically. It shows you that all the electrons are adding up, basically, on both sides. Okay, so in order to create this gamma carboxyglutamic acid, you need vitamin K hydroquinone. However, after you've done this reaction quite a few times, you're going to run out of vitamin K hydroquinone, because it's all going to have become this vitamin K epoxide. So basically, you need a way of regenerating the vitamin K hydroquinone from vitamin K epoxide. And basically, this is done by an enzyme known as vitamin K epoxide reductase, which first converts vitamin K epoxide back to vitamin K up here, and then also converts vitamin K to vitamin K hydroquinone. So it basically does both of these reactions. Okay, so the enzyme which catalyzes this conversion of vitamin K epoxide down here back to vitamin K, and then vitamin K to vitamin K hydroquinone, this is known as vitamin K epoxide reductase. Okay, and this is often abbreviated to VKOR. Okay, or VKOR. So VKOR, vitamin K epoxide reductase. So the V is for vitamin, the K is for K, O is for oxide, so they've missed off the epoxide, but never mind. And the R is for reductase. So it is this enzyme which is inhibited by warfarin. Okay? So if you take warfarin, it will go into the cells of your liver. It will inhibit the vitamin K epoxide reductase enzyme, and that will stop you from being able to regenerate vitamin K hydroquinone from vitamin K epoxide. So gradually you'll use up all of the vitamin K hydroquinone, and it will all be converted into vitamin K epoxide, and you won't be able to regenerate it. So once you've run out of vitamin K hydroquinone, you cannot continue to convert glutamic acid into gamma carboxyglutamic acid, and if you can't do that, then you can't make functional coagulation factor 2, coagulation factor 7, coagulation factor 9, and coagulation factor 10. And if those all go down in the blood, then you're not going to be able to perform the coagulation cascade, because, for instance, 2 is utterly essential. It's thrombin, it's prothrombin. So if you have no prothrombin in your blood, then you certainly cannot make any thrombin, and therefore you can't convert fibrinogen into fibrin, since prothrombin is the thrombin is the enzyme which does that. Okay, so we'll continue this discussion in the next video.